Hey everyone, and welcome to our second lesson in our third unit on phases of matter. Today we're going to expand on our understanding of heating and cooling curves and phase changes, and we're going to introduce the heat of fusion and the heat of vaporization and exactly how that relates to our heating and cooling curves and phase changes. So at the end of today's lesson, you should be able to calculate the heat involved during different phase changes using this heat of fusion and the heat of vaporization. Now we'll start with the heat of fusion, which is a measurement of heat energy. And before we get into that, we're going to do a little review about our calorimetry equation, which is Q equals mc delta T. And this equation helps us determine how much heat is involved during a particular chemical or physical change when we have a temperature change. And we can figure out how much energy is being absorbed or released during that change. But we can't use this calorimetry equation to determine how much heat is required to melt or boil a substance. And if we think about the heating curve, remember these flat portions here on our graph, on our axes we had time and temperature. And on these slanted portions we have a change in average kinetic energy. We have a change in temperature. But on the flat portions, remember these are where phase changes are occurring, we don't have a change in temperature. The curve is flat. And this is where we have changes from liquid to gas and solid to liquid. So if we tried to use the calorimetry equation during one of these phase changes, we wouldn't have a delta T. This quantity would be 0, and therefore the amount of heat using this equation that's being responsible for the phase change couldn't be calculated because of that 0. So to determine how much heat is required to convert a certain mass of solid to a certain mass of liquid, which should be the same, because we have our conservation of matter, we have to look at and investigate the heat of fusion. And it's going to look similar to calorimetry, but since we don't have a temperature change, we're going to kind of disregard that quantity, and we're going to adjust the specific heat capacity, which we use in calorimetry to explain how quickly a substance is gaining or losing heat. And what we're going to do is change that specific heat capacity, in this case to a heat of fusion, and everything else is going to stay the same. So the heat of fusion is how much energy is required to rearrange all the particles of 1 gram of solid, any solid substance, to 1 gram of liquid. And we can also see that in reverse, how we can rearrange 1 gram of liquid to 1 gram of solid. This would essentially be freezing 1 gram of solid to 1 gram of liquid would be melting. So both of these phase changes, again, if we think about our curve, any phase change on this first lower portion where we have solid to liquid, we're going to use the heat of fusion. And we're going to use it in both directions. And it's just going to depend on if it's an exothermic change or if it's an endothermic change. Now this value for the heat of fusion, abbreviated capital H sub F, the value is 334 joules per gram. You find that on table B on the front page of your reference table. And that's how much energy is required when a solid, in this case water, that's the value for water, is melting or liquid is freezing. So for water, for every gram of water, we're going to release 334 joules when we freeze, and we're going to absorb that amount when we melt. So the direction of the heat flow is going to determine which phase we're referring to. So the heat of fusion can either be a positive or negative value depending on if the change is endothermic or exothermic. If we have a net input of heat, in this case Q is equal to heat. We see it in calorimetry as a lower Q. But if we have a net increase in heat into a substance, we're going to have a positive heat of fusion value. This is an endothermic change, which would constitute melting. A net input of energy to rearrange those densely packed solid particles into giving them more energy and causing them to move away from each other, decreasing their IMS. If we have a net output of energy, Q leaving the system or leaving our substance, that's an exothermic change because we have heat energy leaving the system, and this would occur and indicate freezing. As we remove energy from liquid particles to allow them to rearrange, increase their IMFs, and get closer and more densely packed with each other. Well, let's see an example of this. How many joules are required to melt 255 grams of ice at 0 degrees Celsius? Now, when you complete these questions, we want to look for certain indicators in the question that are going to tell us that this is a heat of fusion kind of problem. When we see things like joules, which is indicating heat, that should always direct you towards your heat section on table T. And when you see things like a phase change, when you have melting or potentially freezing, those are good indicators that we're going to use heat of fusion. Or a temperature. 0 degrees Celsius would indicate our phase change, and therefore we would use our heat of fusion. Now the equation we'll use is on our reference tables in our heat section on table T, and it's Q equals M delta HF. And again, our heat of fusion is found on table B, and that's for water. So we know that we're working with 255 grams of water, and this delta HF is always going to be the same value, which we know it as 334 joules per gram. So we're going to plug these in. 255 grams of water, and that amount can change. And we have our heat of fusion as 334 joules per gram. And that we get from reference table B. Now this looks similar to calorimetry. We replace the C value, the specific heat capacity, with the delta HF. And our change in temperature, since we don't have that because of our phase change, we got rid of that. So it's another indicator that we're going to use a heat of fusion when we don't see a temperature change. So we plug in our values there. Our grams cancel. We're left with 85,170 joules, which we would round using sig figs to 3. And we round that to 85.2 kilojoules. You could leave it as joules as well. Both would be sufficient. Now if we take a look at the upper portion of our heating curve, we have the phase change between liquid and gas. In this case, we're going to use what we call the heat of vaporization, because it's going to take more energy to boil and condense a substance than it is to melt or freeze it. And that value, called the heat of vaporization, is how much energy is required to change 1 gram of liquid into 1 gram of gas, or to change 1 gram of gas into 1 gram of liquid. And this value, the heat of vaporization for water, is found on table B. And we can notice that compared to the heat of fusion, 334 joules per gram, the heat of vaporization is almost 10 times as much. means it requires almost 10 times as much energy to boil water than it does to melt it. Which should probably make sense intuitively, because you have gas particles that are moving significantly faster, and in order to get them to move that fast, you have to give them a lot of energy. Now, the heat of vaporization can also be positive or negative, just like the heat of fusion, and it's going to depend on the direction of energy transfer, either an endo or exothermic change. So if we have energy coming into the substance, that's going to be an endothermic change. This is going to be boiling. You have to input energy, a positive value for heat of vaporization, in order to boil a substance. If we have a net decrease in energy, or we have heat leaving the substance, we're going to see a negative heat of vaporization value, and that's going to indicate exothermic change, energy leaving the system. In this case, we'd have gas slowing down. This would be condensing, hot gas condensing, cooling, slowing down into liquid. Now, to see an example of this, again, we want to look for keywords that indicate that we're going to use heat of vaporization, or that can get us to the heat section on table T. So again, we see things like joules. How many joules are required to vaporize? Vaporize should also indicate heat of vaporization. It is a phase change from liquid to gas. We have a mass of water, and we see this last one here, 100 degrees Celsius, which is our phase change for our boiling point for water. That's where a phase change will occur for condensation and boiling, depending on the net energy change. Now, the equation we'll use will look just like the heat of fusion, but we're instead going to use the heat of vaporization, and that's just going to give us a different value. So we plug in how much water that we have, 423 grams, and we use the heat of fusion value, or excuse me, the heat of vaporization value from table B. And this is going to be a much higher energy value compared to the heat of fusion for the same amount of water. Again, almost 10 times as much. So we get a number here of 955,980 joules. We round that to sig figs, 3 and 3. We end up with 956 kilojoules. Both those values work as written. Now, another practice problem. With all of these, feel free to pause the video, try the question, and resume and check your work. Suppose during basketball practice you lose on 910 grams of water due to sweating. If all this water evaporated, how much energy did the water absorb from your body? Now, if you have, I'm going to try and draw a hand here, and it's probably going to look really bad. But that's okay, I don't think that's terrible. At least it has 5 fingers and 1 big thumb and a gnarly pointed index finger. If you have all this sweat on your arm after you're playing basketball, and this is how your body cools itself, you're running around, you're creating all this, converting all this energy into motion of your body, you're overworking your body's trying to cool down. It secretes sweat and moves it to your skin, so this can evaporate, and when it evaporates, it's going to take heat with it, and the heat's being supplied by your body. So in order to evaporate, 1 gram of sweat has to absorb 2,260 joules per gram. This is being supplied by the heat from your body, and this is how your body cools down. It removes excess energy by transferring it into the sweat on your arm, therefore leaving your body and moving your heat into the surrounding environment. Now, if we want to figure out how much energy is absorbed from the body to evaporate 910 grams, well, we look for a couple things here. We see evaporated. We see that we have a mass of water. Evaporate is going to be the key here. This is a phase change from liquid to gas, so we're going to use heat of vaporization. We know the mass of water, and we can solve for how much energy, or the Q value, that's going to require. So we'll plug this in, 910 grams. Our heat of vaporization is 2260 joules per gram. Grams cancel. We end up with a pretty large number, 2,060,000 joules. And we'll round that to 2,060 kilojoules. That's how much heat energy is required to evaporate that 910 grams of water on our skin. We'll do a couple more practice problems with this. Again, feel free to pause the video, try the problem, resume, and check your work. When 20 grams of a substance are completely melted at its melting point, 3,444 joules are absorbed. What is the heat of fusion of this substance? Now the question is asking you for the heat of fusion. And we're not dealing with water here. We're dealing with a substance. So we want to find the heat of fusion. And the heat equation that we have with heat of fusion is Q equals mHf. Which means we should have a Q value and a mass of our substance value. We know that we have 20.0 grams of that substance, and we know that 3,444 joules have to be absorbed. So we take these two values and we plug them in. 20.0 grams times the heat of fusion. We divide. See our units there, joules per gram. We plug this in, and we get a value for heat of fusion about 172.2 joules per gram, which comes out to selection B. Next example. What is the total number of kilojoules required to completely boil 100.0 grams of water at 100 degrees Celsius and 1 atmosphere? The 1 atmosphere we'll get into in our next lesson. This condition can change and does affect the boiling point of a substance. And this is a pressure value. So for this problem, we're looking for a total number of kilojoules, which indicate heat, which should direct you to table T on your reference table, required to completely boil. There's our phase change. 100 grams of water, which we know is a mass of water, at 100 degrees Celsius. Again, boiling point of water indicating phase change. So we're going to want to use our heat of vaporization, given our indicators in the problem. We're looking for the total number of kilojoules required, so our heat value is unknown. We know that we have 100.0 grams of water, and since we're boiling, we're going to use the heat of vaporization at 2260 joules per gram. So we plug in 100.0 grams for our mass and 2260 joules per gram for heat of vaporization. And our Q value comes out let's see, get all my zeros in order here. It's only got one too many. When I cross that out instead of erasing, I apologize for the messiness of that. And when we round this, this comes out to 226. 226 kilojoules. If you guys have any further questions, make sure you write them down and come see me to get your questions answered. Have a great day.